Welcome to Automated Visual Software Analytics. This part is about a software map theme called Error-Prone Code. We will briefly outline characteristics of error-prone code. We will see how software maps can depict error-prone code, and we will discuss application and some actionable insights. Let us start with error-prone code. This phenomenon is one grave quality issue in software engineering and, in particular, for software maintenance. It has many negative effects. Some of them are that high bug fixing costs result for the development, and in particular for operational systems if they have to be fixed. Another negative side effect is the potential damage that can cause error-prone code on the reputation of a product or even a company. Another negative effect is the conflict that arises due to bug fixing activities versus scheduled development activities. And another negative side effect, the impact on the developer team motivation and mood. Now, what are factors for error-prone code? What does cause typically error-prone code? One aspect is software complexity. Error-prone code is correlated with software complexity. That can be measured, for example, by some software quality metrics, such as the nesting level metric, the McCabe or cyclomatic complexity, or the Halstead metrics. Another important factor for software complexity and error-prone code is a simple one. It's the software size. Generally, error-prone code is an inherent property of a large-scale system. That is, error-prone code fractions are somehow proportional to the size of a module. It can be measured, for example, by lines of code metrics. Another factor is the software development itself. Error-prone code also correlates with development activities. Roughly speaking, if many things in a source code unit are changed, then most likely many errors are introduced or are potentially introduced as well. Now, how can we identify such code? Basically, if we take into account these factors, then we can most likely find a good strategy for identifying potentially error-prone source code units. There's no single efficient strategy to identify or catch error-prone code or even errors because, as we all know, they have manifold reasons and they cannot easily be seen because they have a very different appearance. Sometimes it's due to an insufficient test coverage, sometimes it has algorithmic problems, sometimes there might be a technical reason for causing an error. So we have a manifold group of reasons that cause error-prone code. The software analytics approach to catch error-prone code takes into account the factors, namely software quality metrics and development activity. So it correlates these two categories of information about complexity and changes to provide an effective detection of code that is likely to be error-prone. Software maps with a corresponding map theme facilitate then identifying the most error-prone suspected modules. So this is our goal, to have a software map that helps us to identify modules that are suspected to have error-prone code. Here's an example of such a software map. Actually, this is part of a Java-based system, the Android system, and it uses lines of code, logical lines of code, as a base measure for the cuboid's footprint size. The height of each cuboid is defined and determined by the McCabe complexity of the corresponding module. So tall cuboids mean that these modules have a high cyclomatic complexity. And the coloring uses a schema that maps the number of developers to three principal colors: red, yellow, blue. So if we have more than 11 developers in this example, then the cuboid gets red. If there are between 2 and 11 developers, then we have a yellow color, and blue means only one developer operated on a source code unit. So the color expresses activity. More formally, the composition of the software map theme error-prone code uses logical lines of code mapped to cuboid's footprint size, used to expose monolithic code as a first indicator to code that is hard to manage. McCabe complexity, mapped to the cuboid's height, is used to indicate complex error-prone coding due to the cyclomatic or control flow complexity. Number of involved developers that change a given source code unit within a given time frame mapped to a color scheme is used as a measure for bug fixing effort in general. So combining McCabe complexity and bug fixing effort expressed by this development activity guides our awareness towards modules that are highly complex on the one hand, and on the other hand are often touched in the course of bug fixing. So, for example, the red tall cuboids can be easily identified as potential bug fixing hotspots. Yeah, how can it be used and applied? Error-prone source code units should be identified if we use this software map theme and revised as early as possible to reduce the number of error-related incidents in the future. So this is what we can expect, that we reduce this incidents in the future. We can also focus software development activities on highly error-prone code units to maximize the impact of our invested effort with respect to the software quality. So it's a good, let's say, guide to modules that deserve most of our attention in the future software management and maybe refactoring or redesign. We can also precisely adapt our testing activities to ensure that all highly error-prone source code units are actually covered by our test frame. So we can optimize our testing activities if we focus on error-prone source code modules. Potential conclusions and way of proceeding means, first, we have to identify the most error-prone code items in our software landscape, and then we should try to reduce their complexity, as well as we have to ensure proper testing of those items. So at this point, one remark, this is where predictive and even prescriptive software analytics comes in. So based on the software map theme and its findings, we can more or less set up certain measures that help to overcome the identified problems or weaknesses. And the concrete activities lead to the prescriptive aspect of software analytics. Let's summarize this part. We have seen the software map theme, error-prone code, can be applied to get an overview of error-prone source code units. The software map uses software analytics in particular to assist to manage one root cause of low software quality by revealing the correlation of complex code and code changes. And this correlation can be called an unfortunate correlation, because if complex code is handled frequently and quite often, then we can conclude that this these parts are most likely to be error-prone or error-suspect. As actionable insights, this kind of software map guides responsible stakeholders to prioritize those modules that deserve and demand for complexity reduction. Or we can also set up and develop better testing in order to increase code stability, especially code stability in the long run. The approach underlying this software map theme applies the yesterday's weather rule. This rule basically transformed to our problem domain means code items that caused errors in the recent past will most likely be the root cause of future errors. Typically, refactoring measures are adopted for those modules. Of course, there are many activities we can opt for, we can adopt in order to make the stability higher of the source code modules that have been identified as modules that are most likely to be error-prone. This concludes the part about the software map theme, discovering error-prone code.